Hi everybody, welcome back to the Feynman technique. Today we'll be taking a look at this integral that I got off the channel Black Pen, Red Pen. He posted it about a week ago. You don't need Feynman integration to solve this, you just need to know the value of the Gaussian integral and standard calculus integration techniques. But I'll be using Feynman integration, of course. Alright, so let's just start off by making the substitution. X is equal to 1 over u, giving us dx is equal to negative 1 over u squared du. Okay, so that is going to give us is equal to the integral from 1 over 0, which is infinity, to 1 over infinity, which is 0, of 1 minus e to the negative u squared, right? Yeah, all right. And then we'd get times negative 1 over u squared du. And then the negative will be used to switch our bounds. All right. So there's our new representation for I. Okay. Well, to proceed from here, let's use Feynman integration. We'll create a function of t equal to the following. It'll be the integral from 0 to infinity of 1 minus e to the negative tu squared over, no, you know what? I don't want to do that. Let's just make it negative tu squared. I don't know. I just feel like that's going to be a little bit easier. Du, right? And then of course, if we evaluated it at 0, we'd get, well, let's see, this whole expression would become a 1. That's 1 minus 1, which is 0. And then f of 1, of course, would recover our original integral I. All right. Now let's let let's let tu squared equal w squared. Well, that would mean that t to the 1/2 u is equal to w, of course, ignoring the plus minus. And then bringing this to the other side is a t to the negative 1/2. T to the negative 1/2 w. That would give us du equal t to the negative 1/2 dw. All right, rewriting our f of t. And I'm just going to make all our w's x's. I'm just going to bring it back to x. So let's see, is that going to affect our bounds of integration? No, it isn't. And then we'd have 1 minus e to the negative x squared over, well, we still have this u squared. I'm sorry, guys. I'm not going to redo this video, but I did make a mistake. There's no reason for me to jump into that substitution yet, because we actually have to perform the Feynman integration. All right. We're going to take the derivative of this expression with respect to t. That's going to give us f prime of t is equal to the integral from 0 to infinity of, well, let's see. This whole first fraction is going to drop out when taking the derivative with respect to t. So let's see. We're still going to have our exponential expression, which is negative e to the negative tu squared du times the derivative with respect to t of this. Well, that's going to give us negative u squared, and we'll use that u squared, of course, to cancel this. Okay, now let's clean this up a little bit. Okay, that's better. Now let's just go back to x. Let's say that t to the 1/2 u is equal to x. Okay, well, that's going to give us du is equal to t to the negative 1/2 dx. All right, now let's rewrite f prime of t. All right, we'll still have the same bounds of integration, right? Yeah. And then the whole point of that substitution was to turn this into an e to the negative x squared, and then our du becomes t to the negative 1/2 dx. And this part right here is equal to the square root of pi over 4. All right, so our entire f prime of t is equal to the square root of pi over 4 times t to the negative 1/2. All right. Well, let's get back to f of t by integrating both sides or all sides of that expression. That would mean that f of t is equal to the antiderivative of this thing with respect to t. Well, that's going to give us, of course, the square root of pi over 4. All right, that's going to give us t to the negative 1/2 over 1/2, which is just t to the 1/2 times 2, and we'll use that times 2 to get rid of that 4 inside the radical. All right, so there's our f of t, right? No, we need the plus c. Okay, because we were taking an indefinite integral, so we need that constant of integration. All right, we'll use f of 0 equals 0 to solve for c. That's going to be basically, c is going to equal 0, because if f of 0 is equal to 0 and we evaluate it at 0, this is 0, this is 0, and this is c, giving us c is equal to 0. There we go. So f of t is equal to the square root of pi times t to the 1/2. Well, we know that I is equal to our function f evaluated at 1. So I is equal to this evaluated at t is equal to 1, which would simply give us the square root of pi. All right, guys, there you go. That's the answer to that integral. You don't need Feynman integration to solve it, but since this is a channel on Feynman integration, I used it. So there you go. Hope you enjoyed that.